today I want to count indecomposable vector bundles on curves. And this will involve absolutely no geometry. This is purely algebraic. Oops, no. Geometry. And tomorrow, or at least next time, I want to relate it to the number of stable Higgs bundles. And hopefully I will have time to present two proofs, or sketch two proofs. One is geometric, and it somehow uses the symplectic structure. And ideas close to what Victor was explaining today and yesterday. And the other one is again purely algebraic. And one advantage of this other one is that it is not based on the symplectic structure, and it also works for these twisted Higgs bundles, which Thomas Hales was mentioning this morning, at least when the divisor is a high enough degree. And this last one is some joint work with Sergei Mozgovoi. So it's a different second step. Okay, and so what I promised yesterday was to use these categories, or Grothendieck group of categories of Eisenstein sheaves, what I called Eisenstein sheaves, which come from this geometric Langlands conjecture around the trivial local system, in order to count these indecomposables. So let me first introduce some analog of this K0 group directly on the level of functions and not sheaves. So this will be the first part of, well, I have some more space, of today. So I think this is the third one. This is what I call spherical whole algebras of curves. And this whole project of considering whole algebras of curves was initiated by Kapranov in a very nice paper in late 90s. And he was the first one to notice that there's a nice structure on these whole algebras reminiscent of quantum groups, certain infinite dimensional quantum groups. Okay, so let me fix some notation. X is our smooth projective curve over FQ. Let's write the zeta function of x. This is all we will need about x. So the dependence on x is rather small for these spherical whole algebras. 1 minus alpha I z, 1 minus z, 1 minus qz. And let me denote. Let me denote by Koch R D. This is the category of coherent sheaves on X of class RD, so of rank R and degree D. And this whole algebra, the non-spherical whole algebra for the moment, is the following. So HRD is the set of functions from objects Koch RD up to isomorphism to C such that the support is finite. So compactly supported functions on the moduli space, if you want, moduli stack of coherent sheaves of rank R in degree D. This is my vector space, infinite dimensional. And my whole algebra Hx will be the direct sum for all R and D of HRD. And I will use this parabolic induction and restriction, this Eisenstein and constant term operations, to endow this vector space with a Hopf algebra structure. So let me quickly explain this. It's useful to pick a square root of Q. And let me define the multiplication first. So it goes from HRD, tensor HR prime D prime, to HR plus R prime, D plus D prime. And it's given by a formula which is reminiscent of what Dima Rinkin described when he explained the Hecke operators for GLN. So if I have two functions, f and g, I should spit out another function. And this function will take values on f, a coherent sheaf f, given by the following formula. So this is where you have this Euler form appearing. This is some renormalization. You shouldn't worry too much about this factor. And you take the sum over all sub-objects of f of, I won't have time, and I won't have space, g of h, f of f over h. Okay, so if you want to think about characteristic functions of coherent sheaves, this form a basis of your whole algebra. If you unravel a little bit this definition, you will see that the product of the two characteristic functions of sheaves, say h1 and h2, will be supported on the set of extensions of h1 by h2. So in some sense, this encodes all the possible extensions between coherent sheaves. So if you choose one of them to be torsion, then this is exactly what Hecke operators, some Hecke operators for GLN do. And this endows Hx with associative algebra structure. This is very easy to check. Okay, and you can do this for arbitrary abelian category as soon as these sums are finite. So here the sums are finite because we are in the case of a smooth projective curve defined over a finite field. So we need to check this. So this was the algebra structure, the Eisenstein induction. Now we have the coproduct. Coproduct goes from H r plus r prime to H r d tensor H r prime d prime. Here I have to be a little bit careful because if you have two sheaves, there are only finitely many possible extensions. So it really you really have a map like this. But if I have one coherent sheaf, then there might be infinitely many ways of breaking it up into two coherent sheaves. So you have to work with a certain completion of this tensor product. And here's the formula. If I have the function h, then I view this as a function on the product of two stacks, if you want. So to f and g, I associate, there's again this Euler form. Then there's a correcting factor over the sum over the x1 of f and g. And actually what you do, you average over all extensions of f and g, and you get h x xi, and xi, x xi is the extension corresponding to xi. Okay, so this looks a bit less familiar maybe than these, but right now I will introduce the third piece of data, which is the so-called pairing. Well, in the theory of whole algebras, it's called the green pairing, in honor of this famous mathematician who unraveled representation theory of GLN of FQ in the 50s and then came back 40 years later to define this pairing in the context of whole algebras. So what is this pairing? It's very simple, very natural. I have two functions, and f of g is simply just the integral of fg. And the way to write it here is you take the sum over all sheaves, f of f, g of f, divided by the number of automorphism of f. But really, this is just integral of fg. Okay. You can choose also the Hermitian pairing, but maybe it's more natural, but I will stick with this one. And the fundamental theorem is the following. So this is what Green proved. And Ringel studied the algebra structure before. It says the following. If you look at this algebra, HM, and the co-algebra, and you have this Green pairing, this is a self-dual Hopf algebra. And I am cheating a little bit. This is a topological Hopf algebra because the coproduct lands in a completion, but this is not really a problem. And also not a problem is the fact that you have to twist a little bit the product in order to actually get a Hopf algebra. And what does it mean to be a self-dual Hopf algebra? It means that you have this non-degenerate pairing which satisfies the following property. If I have Fg against H, then this is the same thing as F tensor G against delta of H. So in other words, this says that these two operators, multiplication and co-multiplication, are adjoint. And so this is forced to us if we want to have such a nice property. Okay.
But you mean tensoring by the group algebra of velocity group?
Yes. Yes. Or you can just twist the product structure on this tensor product, on H tensor H, like Lustig does. Okay. Now, what is the spherical whole algebra? And this is all that we need. So this whole algebra right now is related to all automorphic forms. On the automorphic side, this is the classical version, functions, but everywhere. And I'm only interested in things related to the trivial local system, which means that I have to pick a smaller subalgebra. So this spherical whole algebra is defined to be the subalgebra generated by some very simple functions, namely the set of all characteristic functions under pic D, where D is in Z, and the set of all characteristic function of coherent sheaves of rank 0 and degree D, when D is now positive. Okay, so this generates a certain subalgebra, and you have the following proposition. So first, this spherical subalgebra is also a self-dual Hopf algebra with the same restrictions as before, but it is a Hopf subalgebra, stable under the coproduct, and it's also self-dual. And the second thing, which will look a bit technical here, but those of you who know about automorphic forms will see the relevance. You can consider what's called a constant term, which is the parabolic restriction to the torus. And in this language, it means if you restrict it to h, x, r, let's say spherical, this is just you take the coproduct, iterated r times, and you want to land into degrees 1, 1, 1, 1. Okay, so you take a rank r bundle, and you take the r-fold coproduct, and you just look at the component which lives in rank 1, 1, 1, 1. Okay, so this goes from hx spherical of degree r to hx spherical of degree 1, tensor product with itself r times. And the statement is that this is injective. So when you try to decompose automorphic forms, then the piece that is usually most interesting are the cuspidal functions, and they are precisely in the kernel of these kind of maps. But our setting is orthogonal to cuspidal functions, and so actually this whole algebra, when you restrict this constant term map, this is injective. This is very convenient, and it actually helps you to have a concrete combinatorial realization of this whole algebra as what's called shuffle algebras. But I'm not going to talk more about this. I will still make a few remarks concerning interpretation in terms of automorphic forms, if you want, in the language of automorphic forms. So, remarks. First one is that this whole algebra contains two natural subalgebras. One is subalgebra corresponding to functions supported only on vector bundles. So this would be Hx bun, a set of functions in Hx such that the support of f is inside vector bundles. And you can consider the orthogonal thing, namely those functions whose support, well, this is just a direct sum for all d of h x r 0 d. So those functions whose support is on the torsion sheaves. And so the first one, this is exactly the definition of everywhere in ramified automorphic forms. So this is, I'm not going to write the whole thing. I'll just say automorphic forms for GLR, and it's the direct sum over all R, unramified. And this piece here is related to the Hecke algebra. So this is the algebra of Hecke operators. And somehow this is you would like an algebra of Hecke operator for each GLR, but you can put them in a tower. And this is maybe the algebra of Hecke operators for GL infinity. So here we are in the pathological world of type A. So we have lots of strange things happening. And this algebra acts on this algebra by the Hecke operators. And you can write Hx as the tensor product of the bundle part and the torsion part. So from the point of view of automorphic forms, this whole algebra mixes something which is usual, the automorphic forms, even if you take the sum for all GLR, but it also adds inside the algebra the Hecke operators. And this makes the formulas much nicer if you put the two together, as we will see. And then I have to relate this briefly. To what I said yesterday, this category of Eisenstein sheaves. So this is my second remark, is that via the Fizeau function correspondence, so taking trace of Frobenius, correspondence, and up to completion, this spherical whole algebra corresponds to the direct sum of this K0 of the category of Eisenstein sheaves for GLR if you take them over all coherent sheaves and not just vector bundles. And here I am cheating a little bit because morally it's certainly true, and you can work with this algebra and you get a lot of things already. But to actually prove that the trace of these simple perverse sheaves will generate this algebra is not easy. And I don't know how to do it in general, just in some small genius cases. Okay, so I want to state one result here, one proposition, which explains that this algebra really only depends on the zeta function of the curve and not on the curve itself. And the way to formulate it is to say that there is a universal or integral form of this whole algebra. So let me, first of all, I have this statement. For any alpha R, so these are classes, and you index them in such a way that the slopes are increasing. You can look at the characteristic function of the Hardan-Narasimhan strata associated to alpha, and you can prove that this belongs to the spherical whole algebra. So somehow you can get this characteristic function of Hardan-Narasimhan strata by some good combination of induction or Eisenstein induction of these one peak D. This is the first part of the proposition, and then the second part of the proposition is about this integral form. So recall the notation Tg and WG from last time. And I will define Rg is Q of Tg Wg. So if you remember, this is Q of Z1 Zr satisfying the relation Z2i minus 1 Z2i is Z2j minus 1 Z2j, and you take the invariant under this Weil group of the general symplectic group. And so the theorem is that there exists a Rg Hopf algebra. Let's call it H spherical R, Rg, containing elements one R Hn alpha. So I can have an integral form, and this integral form also contains these guys, such that for any finite field Fq, for any x, the spherical whole algebra of x is isomorphic to the specialization of this universal whole algebra, where the Zi go to these Frobenius eigenvalue. And of course, the specialization of this characteristic function of Hardan-Narasimhan strata go to the actual characteristic function of Hardan-Narasimhan strata. And this Rg Hopf algebra has a pairing and so on. So this is a way to say that this Hopf algebra, the spherical one, is somehow flat over the moduli space of curves of genus G. Okay, so now that I defined all these, let me try to do something with it, just to show you how it can be useful. And also this will be a good illustration of what's to come in the second part of this talk. So for this, I have to introduce Eisenstein series. So after all, this whole algebra is built out of Eisenstein product of some very simple functions. But so far I haven't talked about Eisenstein series, but it's made so that it contains Eisenstein series, a particular kind of Eisenstein series. So let me give the definition here. Let me define ERZ is the sum for all D of the constant function on the whole stack Rd, And I have to renormalize it a little bit. And this, you can think of it as belonging to a big product over all z of some completion, because this is not a finite support, of some completion of the whole algebra. Okay. And you can restrict yourself to bundles if you want. And you can do the same. And why do we consider such things? Well, it's clear that it's easy to check that this is a Hecke eigenform. And why do we have to consider all these components? Because if you remember the Hecke operators, they go from one component to the other. They change the degree. And so we have no choice. If we want to have a Hecke eigenfunction, it has to live in all degrees. And this is the simplest possible way to construct a Hecke eigenfunction. Just take the constant function. Okay. And then these are just generating functions for the constant function, if you want. But the interesting thing to do is to multiply them so that you produce other Hecke operators, other Hecke eigenfunctions. It's easy to see that if you multiply two eigenfunctions for Hecke operators, then you will still get an eigenfunction for Hecke operator. So you're really tempted to consider products of these big series. So let's write ER1 Z1, ERS ZS. This is the Eisenstein series. Well, at the moment, all you can say is that it belongs to a product of spherical whole algebra. And you have all these coefficients, which could go to infinity in both directions. So it seems a rather nasty space. But there's a classical theorem due to Harder, which says the following. This big series, actually, when you evaluate at any given coherent sheaf, it's not a series which is infinite in both directions. It's only infinite in one direction. And even better, this is the expansion of a rational function. So really, you can make sense of it as a rational function. So for any f in Koch R D, if you evaluate Rs, Zs at f, this is the expansion. This is the expansion in the region Z1 less than Z2 less than Zs of a rational function. Okay, so this is very nice. It gives sense to these big products. And it also allows you to write down some relations between these Eisenstein series. So let me write a bunch of very nice and simple looking.
Can you say a word about how this is proved, the rationality?
Not on the top of my head. But it's not obvious. It's not completely obvious. So the way Harder proves it, he writes everything in terms of this double coset. But if you think about it directly in terms of coherent sheaves, it's not so clear. It means that there is some kind of periodicity in the number of subbundles, depending on the degree. Yeah, I'm sorry, I don't remember. Okay, so let me write some relations between Eisenstein series. So let me phrase them as functional equations, although only one of them is really called a functional equation. Okay, first of all, this is completely silly. ER of Z, you can split it as the bundle part. And functional and the Eisenstein series for 0. This is silly. This one is also silly, but it looks a little bit more intimidating. If you take the constant term of such a ER, then you get just a product of ERs. You have a little shift occurring, but and here you have V power 1 minus G, R1, R2, and here R1 plus R2 is equal to R. So essentially the constant term of the constant function is again the constant function. Okay, now a little bit better is the following relation, which tells you that this is a Hecke eigenfunction for the Hecke operator. So you can write it like this. This is the product it's a product of zeta functions times ER W E0 Z. Okay. And this is the eigenfunction, eigenvalue if you want. So this is where the zeta functions start appearing. And then there is the actual functional equation, which tells you how to commute E1Z and E1W. And this is really nice. The formula is so simple. 2G minus 1, E1W, E1Z. So there is a little bit of subtlety involved here. Namely, here, this series converges in the region where Z is much smaller than W. Here, it converges in the region where W is much smaller than Z. But this is an equality of rational functions. So you develop the same rational functions in two regions. And you find this equality. Okay. So now what can we do with these functional equations? Let me give one application, let me sketch one application, which is the computation of the volume of Bunn GLR, so the Siegel formula. So it's based on the following very nice result, again of Harder. So first I start with some notation. The zeta function has a pole at q minus 1, but you can somehow renormalize this and write zeta tilde of q minus 1. Okay, and then the theorem of Harder is the following. It says that you can construct the constant function on Bunn RD as an Eisenstein series built out of only E1s by taking an appropriate residue. So here's the formula. If you consider the residue, Z1 over Z2 equals ZR minus 1 over ZR equals Q minus 1. So you take a certain residue of this Eisenstein series, right here you just take the bundle part. Then this is equal to, up to a factor, there's a power of V. I'm sure I'm running out of time, so I'm not going to write it. Q minus 1 power R minus 1. And here you have, in the denominator, you have this product of zeta functions, which occurs in this Siegel formula, times just the constant function. Did I call it Vec or Bunn? Bunn. Okay. Bunn of ZR. So what does it mean? it means that we can get the constant function on this moduli stack of GLR bundles by counting all flags of subsheaves. This is what this Eisenstein product is, and taking an appropriate residue. So I will illustrate right now why this is useful. Maybe I first sketch the proof of this result. This is actually very simple to prove now. Because the idea is very simple, and even the details are not. You have to be a little bit careful with completions and so on, but really it's not so complicated. So what is this sketch of this proof? Well, you just compute the constant term of this residue, E1 of Z1, E1 of ZR, and you compute the constant term of E ben R ZR. And how do you compute the constant term? The constant term is just the coproduct. So you just have to take the coproduct of some iterated coproduct of this product. And if you use these formulas, you see that whenever you apply the coproduct to E1, you get something in E1 tensor E0. And then when you multiply out all the coproducts, you'll have products E0, E1s occurring. And then you use the fact that E1 is an eigenfunction for E0. And this is where all these zeta functions will pop up. So it's a computation, but it's not a difficult one. And you use the fact that CT is injective on the spherical whole algebra. Okay, so this is where this injectivity is nice and useful. And how to deduce the Siegel formula from this? How to deduce the Siegel formula? I think it's the same trick that Langlands used in the number theoretic setting, if I understand well. So let me sketch the proof. Of Siegel's formula. Well, what is the volume of Ben RD? By definition, it's the pairing of the characteristic function of Ben RD with itself. But now we use this fact that we can construct Ben RD as a residue of a big Eisenstein series. And so this is a certain residue of E1 Z1, E1 ZR against 1 Ben RD times times this constant C here. All right, let's say this big thing is the constant C. And now we use the Hopf pairing. The Hopf property of this pairing, the adjointness, if you want, between induction and restriction. And this is C times the residue, E1 Z1 tensor E1 ZR against the constant term of 1 Ben RD. But this constant term is essentially, I'm cheating a little bit, but it's almost, 1 Ben 1 tensor 1 Ben 1. Of course, you need the degrees to add up, but in any case, this is very simple to compute, this constant term. And so in the end, actually, this term almost vanishes, and this is why you have this C appearing here. Okay, so this is the one proof of Siegel's formula, and it really only uses some very simple algebraic properties of these Eisenstein series, and none of these are difficult to prove. This one looks a little bit hard, but in fact, Ed Frankel almost gave the proof in his talk. Okay, so this was an illustration of the use of spherical whole algebra to compute the volume of Bun GLR using these nice algebraic manipulations. Now I would like to compute, well, ideally it would be the volume of Higgs, but first I will use this kind of machinery to try to compute the number of indecomposable vector bundles. So let's see how much time I have. Okay. All right. Now let's see what. Okay, so yesterday I was a bit stressed up by time, and I'm afraid today I will be even more stressed up by time. But still, let me define exactly what is indecomposable bundle, counting indecomposable vector bundles. Okay, so first recall that the category of coherent sheaves over X, this is a Kohl-Schmidt category, which means several things, and among which the fact that every object can be decomposed as a direct sum of indecomposable objects, and these indecomposable objects are unique up to permutation, even though the decomposition is not. And so you say V core X is absolutely, so indecomposable means you cannot decompose it, and it's absolutely indecomposable if V tensor FQ bar is indecomposable. Okay, and so what we want to do is we define A, R, D of X. This is the number of absolutely indecomposable vector bundles on X of class R, D, up to isomorphism, a number of isomorphism classes. And the question is how to compute this number. So let me make a first remark. First of all, this number is finite. This number is finite, and I won't explain the proof, although it's not terribly difficult, but the idea is that a vector bundle which lives on the two degenerate Hardar-Narasimhan strata has to split. So only finitely many Hardar-Narasimhan strata can carry indecomposable bundles. So a bundle which is too unstable has to split as a direct sum. So this number is finite. Let me give some examples. So R equals 1 is not going to impress many people. But so A1 dx, this is just the number of points in peak D. This is a product of 1 minus alpha I. So last time I stated a theorem that said that such numbers were polynomials in the Weyl numbers of the curve. So here we see it's obviously true. If G equals 0, A R D is equal to 1 if R is equal to 1, and 0 if R is different from 1. I'm not counting torsion sheaves. This is not very fun. This is Grothendieck's theorem. Every vector bundle on P1 splits as a direct sum of line bundles. And then for G equals 1, more fun, we have Atiyah's theorem, which implies that ARD is actually equal to the number of points of the curve. So this is 1 plus Q minus the sum of the alpha i's for any R and D. So here you already have the first non-trivial example. And again, it's a nice integral positive expression in the minus alpha i's. Okay, now let me give the formula for rank 2. So formula coming from the theorem I stated yesterday. And now you will see already in the arbitrary genus case, there is a formula which is somehow, how to say, uniform in G, but it's quite ugly. Well, it depends. Once you have seen it 100 times, you end up liking it. So this is A, G, 2, D is equal to, so product 1 minus Q alpha I divided by Q minus 1, Q square minus 1 minus product 1 plus alpha I divided by 4, 1 plus Q plus product 1 minus alpha I 2 Q minus 1 times 1/2 minus 1 over Q minus 1 minus sum 1 over 1 minus alpha I. And it doesn't look obvious at all, but this still belongs to this ring. It's still positive and integral and long. And you can observe that this is independent of the degree D. So this is not obvious. From the geometry, it's clear that if you tensor an indecomposable vector bundle by a line bundle, it remains indecomposable. But if you tensor a rank 2 bundle by a line bundle, you change the degree by an even number. So really, this D here is an element in Z mod RZ. And the claim, the conjecture, and here you can see it, is that it's independent of D for any R. And this is not clear from the formula, which I might give probably next time. So let's see, how much time do I have? I have 10 minutes. So let me make one more remark concerning Quivers. So let me be very brief. For Quivers, I just refer to the work of Katz. So Katz proved exactly a theorem like that, proved the existence of polynomials counting in decomposables. And so from that point of view, it's not very surprising. But from another point of view, it's a bit strange, because what you're doing here is seemingly, it's a strange question to count in decomposables, because the number of, say, absolutely indecomposables would be the sum for all the number for over all indecomposables, absolutely indecomposable, of 1. And this is not the same as the sum for all absolutely indecomposable of 1 over the number of automorphism of F, which would be the volume of the substack of, let's call absolutely indecomposable. And this would be a constructible substack of Bun, GL R, R, D. So here you're claiming that the number of absolutely indecomposable bundles behaves like the number of points of some algebraic variety, which would be very pure and so on. And, well, at first sight, it doesn't look at all like counting the number of points of some algebraic variety, because it would not be an algebraic variety. It would be a constructible stack. And then counting the number of points on the stack, you'd have to include all these 1 over automorphisms. So it seems you're doing something a little bit crazy here, but since Katz was able to obtain so nice results about this, it's genuine to expect also nice results here. Okay, so how do we go about computing this number of absolutely indecomposable using kind of ideas like Eisenstein series? So the first idea, and it works for Quivers, is to count all representations, count all vector bundles up to isomorphism, and then use some recursion. Kind of like the Haldane-Narasimhan recursion, except that now we are not counting semi-stable bundles, but indecomposable bundles. So you can try to do that, but the problem, which you run into immediately, is that the number of vector bundles is infinite. So of given class is infinite. So it's hard to do something with that. And so the solution is you have to find a truncation. Find a good truncation of the set of bundles or coherent sheaves, or maybe the whole category. Find a truncation, and then count all bundles. Count all bundles in this set. So find a truncation, let me denote it like this, of Koch X, and count all bundles in Koch X. And then you can use some kind of Haldane-Narasimhan recursion. So if you can find a nice category, a nice subcategory of coherent sheaves, which will behave well with respect to direct summons, for instance, and if it has finitely many indecomposables, then you can try to apply this kind of arguments. And if you can count the number of objects in this category and find something which would be polynomial in the Weil numbers, then you would be done. Okay, so this is the idea, and I'm sure I have 1 minute. No, I have 5 minutes. Okay, so let me describe this truncation. So this truncation needs two things. It needs to be well behaved with respect to indecomposables, and also you should be able to count all bundles inside. So two conditions. So let me define the mu min of a sheaf F is the slope of alpha 1 if the Hn type of F is alpha 1, alpha S. So in other words, it's the minimal slope occurring in the Haldane-Narasimhan infiltration of F. And let me denote by Koch 0 of X is the full subcategory of coherent sheaves satisfying mu min is greater or equal to 0. So this is the truncation which I want to consider. And some simple facts which are useful is that this category is stable under extensions, quotients, and direct summons. So therefore, you can count the number of indecomposables, and you have this A greater or equal to 0, Rd of X is the number of absolutely indecomposables in Koch greater or equal to 0 of rank R and degree D. Okay, and another fact is that if you manage to compute A greater or equal to 0 RD, then you also get A greater or equal to 0 R. So A greater or equal to 0 RD X is equal to A RD of X for D sufficiently large. There's an explicit bound. But essentially, this comes from what I said earlier, that the Hardana-Riemann, an indecomposable bundle, can only be supported on close Hardana-Riemann strata. So if your degree is very large, and if you're indecomposable, then the minimal slope cannot, at some point, will have to be greater than 0. Okay, so it's enough to compute these things, and therefore it's enough. I'm being a bit quick here. It's enough to compute the volume of Koch 0 RD of X for any RD. And then you can use this recursion that I'm mentioning a bit quickly here, and you will get A greater or equal to 0 RD, and then you can extract out of this ARD essentially by taking a residue. Okay, so now I want to compute this thing, and I really don't have much time, but let me just say that this is done by considering a Jordan decomposition, a stratification, done by considering a partition, done by considering a partition of a certain stack, of the stack. Let me denote it by nil R dx. This is the set of all pairs of F and theta. Now, F is a coherent sheaf of rank R and degree D, and theta is a nilpotent endomorphism of F. So you can think of it as a twisted Higgs bundle with a trivial divisor if you want. Such a pair has a Jordan form. You just look at the Jordan canonical form of this theta. You can make sense of this. And this gives you a partition for nil. And you can count each piece of this partition. So you can have nil R d of x is a partition of all Jordan form of Jordan alpha. And what you're interested in is really nil R greater or equal to 0, which is the set of pairs where F is in this category of coherent sheaves. And so this also admits a partition. And the point is that this is what you compute using Eisenstein series. Using Eisenstein series. And now you have to compute Eisenstein series of a slightly different form than in the proof of the Siegel formula. Namely, you have to consider Eisenstein series which are truncated in the sense that you want to compute this against E R greater or equal to 0 W. Or maybe let me write it. The sum of 1, well, let's just forget about the sum. 1 R D, 1 Koch greater or equal to 0 R D. Okay, so before we had to compute this Eisenstein series on the whole moduli stack of coherent sheaves. And it turns out that when you use this stratification, what you really have to compute is not the volume of the whole moduli stack, not the Eisenstein series paired against the volume of the moduli stack, but only the positive coherent sheaves. And the point is that all this makes sense in this generic spherical whole algebra, because this is a product of, this is a sum of characteristic functions of Haldane-Arrasimon strata. So this can compute in this ring, this generic ring. And you can also get an explicit formula. And I wrote for you the formula in rank 2. So this is how you can use ideas from Eisenstein series to compute the number of indecomposables. Okay, sorry for a sloppy ending.